Today I will explain how the thermodynamic temperature scale is developed using reversible heat engines. It uses energy flow between the heat reservoirs and how efficiently engine operates between them. In this diagram, which is the figure 641, we see two reversible heat engines working between two thermal reservoirs. The first one is one at 1000 Kelvin and another one at 100 Kelvin. Both engines have the same efficiency. Even if they are designed differently or use different working substance, this tells us that efficiency depends only on the temperatures of the reservoirs, not on what's inside the engine. This is what's Carnot principle in action. Second diagram with the figure 642. Here we have three reversible engines, which is the A, B, and C, connected to three reservoirs at three temperatures, which is the T1, T2, and T3, where T1 is the hottest and the T3 is the coldest. So engine A works between T1 and T2 and absorbs heat Q1, while engine B works between T2 and T3 and absorbs Q2. Each engine does work and rejects heat to the cooler reservoir. From this setup, we can confirm that the relationship like Q1 over Q2 equals to FT1 T2. And we find that Q1 over Q3 equals to Q1 over Q2 times with the Q2 over with Q3. This means that the ratio of heat flows depends only on temperatures. So we define a new temperature scale where temperature is proportional to heat transfer. This leads directly to the Kelvin scale, which is based purely on physical law.
Today I'll be explaining the thermodynamic temperature scale, which is rooted in the second law of thermodynamics. This law tells us how energy moves, especially when heat flows between objects or systems. In a reversible heat engine, which operates between two temperature reservoirs, the amount of heat transferred is related to the temperature of those reservoirs. This relationship can be written as QH over QL equals to F times DH over F times DL. Here, QL and QH are the amounts of heat absorbed and released, and DH and DL are the temperatures of the high and low reservoirs. Lord Kelvin proposed that the function Ft is simply T itself. This gives us QH over QL equals to TH over TL. This is the foundation of defining a temperature scale that is not based on physical substance but on pure thermodynamics principles. This brings us to the Kelvin scale, also known as the absolute temperature scale, unlike Celsius or Fahrenheit. The Kelvin scale begins at absolute zero, where molecular motion theoretically stops. On these scales, temperature is defined using reversible processes, making it universal and independent of the working substance. For example, we can convert Celsius to Kelvin using the equation. Just plus the temperatures in degrees Celsius with 273.15. These scales ensures consistency when calculating energy, heat, and enthalpy, and is the standard used in physics and engineering. The visual here shows how an ideal heat engine helps define temperature thermodynamically, rather than using materials like mercury or alcohol thermometers. To summarize, the thermodynamic temperature scale gives us a reliable way to measure temperatures based on physical law, not materials. The Kelvin scale is essential because it provides a universal, consistent method to study energy and enthalpy. It helps define the maximum efficiency of heat engines, and it's widely used in science and engineering for accurate thermal analysis. Understanding this concept not only helps us solve physics problems, but also connects to real-world application in power plants, refrigerators, and even climate science.
the quality of energy. High temperature thermal energy can be converted to work more efficiently than low temperature thermal energy. This means the higher the temperature, the higher the quality of the energy. For example, energy stored in large bodies of water like solar ponds at 350 Kelvin has a very low efficiency under 5%. For conversion to work, make it less competitive for power generation due to the cost and maintenance. Work is a more valuable form of energy than heat because 100% of work can be converted to heat, but only a fraction of heat can be converted to work. The second law, thermodynamic, especially the concept of enthalpy, explains that high quality energy like work is converted to low energy like heat and eventually into useless energy at the lowest quality level. This degradation of energy quality is part of why energy resources are depleted and why pollution occurs. The concept of energy quality is important in various fields, including engineering, economics, and even in understanding daily life choice, such as prioritizing activities based on their quality or value.
Okay, today we will explore what is the Carnot heat engine efficiency. It is a theoretical heat engine operating on a reversible Carnot cycle. The purpose for Carnot heat engine efficiency is to set the maximum possible efficiency a heat engine can achieve. So, from theoretical value, we know that Carnot efficiency is 0.7. So, how do we get this? So, by substituting the value of temperature of low temperature reservoir, which is 300 Kelvin, and then temperature of high temperature reservoir, which is 1000 Kelvin, into efficiency reversible formula, which is 1 minus temperature low over temperature high, and then we can get 0.7. So why do Carnot efficiency matters? So from the diagram, we can see the perfect Carnot engine gives 70% efficiency, while a real engine only gives 45% efficiency. And the third one is an impossible engine claims 80% efficiency. The maximum efficiency depends on the temperature. For 1000 Kelvin hot and 300 Kelvin cold, 70% efficiency is the absolute limit. Real engine cannot reach 70% efficiency because they lost energy as friction, and then 80% efficiency is impossible because it breaks physics law. Remember, Carnot 70% efficiency is nature's limit. Real engines do less. Better than Carnot cannot exist.
Okay, so TL equals to 30 and we have TH equals to 652 degrees Celsius. So we have to use the NTH equals to 1 minus TL over TH equals to 30 plus 273 over 652 plus 2. Why we have to add 273? Because we have to convert it into Kelvin. So the answer is 0.672. Q L equals to T L over TH QH. So T plus So the answer is 164 kilojoule.